In our last video, we defined what the limit of a function was. And in this video, we're gonna work with the properties of the limit so they can make our calculations easier. The first proposition we're gonna see is the unicity of the limit. We have a function f that is defined in an interval ab, except perhaps in a point x0. This is because remember that for the limit of f doesn't have to necessarily be defined in the point where we want to calculate the limit. So now if we have two numbers, L1 and L2, which are both limits of f in x0, then we're going to prove that L1 has to be the same to L2, that is, that the limit of f is unique. Let's go ahead and do the proof. We first start by defining an epsilon that's greater to 0 so we can use a definition of a limit. Now if epsilon is greater to 0, then epsilon over 2 is also greater to 0. And we know that the limit when x tends to x0 of f of x is equal to L1. So then we know that there exists a number delta 1 greater to 0 such that if we have that x minus x0 is smaller to delta 1, then f of x minus the limit L1 is smaller to epsilon over 2. We also know that the limit when x tends to x0 of f of x is L2. So then there exists a delta 2 greater to 0 such that if x minus x0 is smaller to this delta 2, then f of x minus our limit L2 is smaller to epsilon over 2. So now we're going to define delta equal to the minimum value between delta 1 and delta 2. Then if x minus x0 is smaller to delta, we're going to have two things. First, that x minus x0 is smaller to delta 1, and second, that x minus x0 will be smaller to delta 2. Now let's try and make L1 minus L2 as small as possible, because if this is very small, then it means that L2 and L1 are very similar. We can write this as the absolute value of L1 minus f of x plus f of x, and we can do this because this is equal to 0 minus L2, and this is smaller than or equal to, using the triangular inequality, to L1 minus f of x plus the absolute value of f of x minus L2. We can rewrite this as f of x minus L1 plus f of x minus L2. And now, because we have that x minus x0 is smaller to delta, and then x minus x0 is smaller to delta 1, then we have that f of x minus L1 is smaller to epsilon over 2. So we can make this smaller to epsilon over 2. Plus, and now we have that x minus x0 is smaller to delta 2. So f of x minus L2 is smaller to epsilon over 2. So again, we can bound this with epsilon over 2, and then epsilon over 2 plus epsilon over 2 is epsilon. So we were able to make L1 minus L2 smaller to any real number, and this means that L1 is equal to L2. Now let's continue with another theorem. The sandwich theorem is very similar to the one we had for sequences. We have three functions, f, g, and h, that satisfy this inequality. G and h have the same limit, L, in x0. And so the limit of f of x has to be L. Let's go ahead and do the proof. We define first, as always, an epsilon greater to 0, and we write the definition of these two limits. The limit of g of x is L, so then there exists a delta 1 such that if x minus x0 is smaller to delta 1, then g of x minus the limit is smaller to epsilon. Now the limit of h is also L. So then there exists a delta 2 such that if x minus x0 is smaller to delta 2, then our function h of x minus its limit is smaller to epsilon. Now, what g of x minus L smaller to epsilon means is that minus epsilon is smaller to g of x minus L and smaller to epsilon because we have an absolute value. And the same happens with h of x. So now we have two deltas, and we want with f to both these things to satisfy. So again, we're gonna take a new number delta equal to the minimum between delta 1 and delta 2. So then if x minus x0 is smaller to this delta, both these things will be satisfied. And then what we have is that minus epsilon, we said it was smaller to g of x minus L. But now, because we have here in the hypothesis that g of x is smaller to f, here we're gonna have that g of x minus L is smaller to f of x minus L. And because in our hypothesis we had that f of x was smaller to h, then here we're gonna have that f of x minus L is smaller to h of x minus L. But again we have here, so h of x minus L is smaller to epsilon. So then f of x minus L is between minus epsilon and epsilon. This is the absolute value of f of x minus L is smaller to epsilon. And then by definition, we were able to find a delta such that if x minus x0 was smaller to this delta, f of x minus L was smaller to epsilon. So that is the definition of the limit when x tends to f0 of f of x equals to L. Let's go on with the next proposition. We have two functions, f and g, with limits L1 and L2 in the same point x0. So what we want to see is that the limit of the sum of f and g is the sum of the limits. Let's go and prove this. Again, this proof is very similar to the one we did for sequences, so if you remember that, you can just jump ahead and go on with the next proposition. So as always with limits, we start with let epsilon be a number greater to 0, and in this case, because we're gonna have the sum of two things, we know we're gonna have two things that are smaller to epsilon, and so to make the notation easier, we say, well, epsilon over 2 is greater to 0. And now we work with the definitions of limits for f and g, but instead of using epsilon, we're going to be using epsilon over 2. So now we know that there exist two numbers, delta 1 and delta 2, both greater to 0, such that we have two things. If x minus x0 is smaller to delta 1, then this is the definition of limit for f, then the absolute value of our function f minus its limit L1 is smaller to as we said before, epsilon over 2. And using the definition of the limit for g, we have that if x minus x0 is smaller to delta 2, then the absolute value of g of x minus the limit L2 is again smaller to epsilon over 2. And as we've done previously, we're going to take delta, the minimum between delta 1 and delta 2. So then if x minus x0 in absolute value is smaller to delta, both these things will be satisfying. And we want to see the limit of f of x plus g of x. We want to prove that the limit of the sum is actually the sum of the limits, so L1 minus plus L2 in absolute value. If we can make this smaller to this epsilon, then the proposition is valid. We can rewrite this as f of x minus L1 plus g of x minus L2. And now, as always, we can use the triangular inequality, and so we have that this is smaller than or equal to f of x minus L1 in absolute value plus the absolute value of g of x minus L2. And now, as before, we can make each of these terms smaller too. In the first term, epsilon over 2, and in the second term again, epsilon over 2. And the sum of these two terms, epsilon over 2 plus epsilon over 2, is epsilon. So we made this smaller to epsilon. And that is exactly the definition of the limit of x to x0 of f of x plus g of x is L1 plus L2. And this is going to be very, very useful in finding limits of sums of functions. We're not going to see another proposition about the product of two functions. So again, we have f and g, two functions, with limits L1 and L2 in the same point x0. Now we want to prove that the limit of the product between f and g is the product of the limits. The proof is similar to the one we saw for sequences, but it's a bit more complicated, so I recommend that even if you have seen the other one, you stay and look at this one. Again, we have to start with let epsilon be a number greater to 0. Let's first write the thing we have to bound, that is f times g minus the limit L1 times L2. We want to try and make this smaller to epsilon, so let's first work a bit on this expression. We have f times g, and we're gonna subtract f times L2 and then add it again. As always, we can do this because this is equal to 0, and adding 0 to an expression will not change its value. And we have again minus L1 times L2. Now we can rewrite this as taking common factor f from these two terms. Have f times g minus L2 plus, and now here we can take common factor L2, and we have f minus L1. Now we can use the triangular inequality and say that this is smaller than or equal to f times g minus L2 in absolute value plus the absolute value of L2 times f minus L1. Now we have a product, and the absolute value of the product is the product of the absolute value, so we have to take f outside, and we have the absolute value of f times the absolute value of g minus L2 plus the absolute value of L2 times the absolute value of f minus L1. So now we have a few things that can be made small. G minus L2, we have the limit, so we can make this smaller to epsilon, and the same with f minus L1. But these two things are multiplied by an f, and by L2. The L2 won't affect much because if we can make this smaller to epsilon, then we can make it smaller to epsilon divided by L2 or epsilon divided by 2 times L2 because we have a sum and we in the end want to have in this whole term an epsilon over 2. But here we can't make it smaller to epsilon over 2 times f because then it would depend on x, and we can't do that. We talked about this in our previous video. So we have to try and first bound the f. And so for this, what we're going to do is first observe that the absolute value of L1 is smaller to the absolute value of L1 plus 1. And with this, it is actually very easy to prove that there exists a delta 1 such that the absolute value of f of x is smaller to L1 in absolute value plus 1. And this will happen for all x such that x minus x0 is smaller to delta 1. This is easy to prove, so I will leave it as an exercise. Now, as we said before, we can make these two terms small using the definition of a limit. So we know that there exist delta 2 and delta 3 greater to 0 such that using the definition of limit for f is that f of x minus L1 will be smaller to epsilon over 2, and here I'm going to divide by L2 because we have it here, and then we can cancel this one with this one out and we'll just have epsilon over 2. This will happen only if x minus x0 is smaller to, say, delta 2. But also, using the definition of the limit for g, we know that the absolute value between g of x minus L2 will be smaller to epsilon divided by 2 times the absolute value of L1 plus 1, because that is the bound we were able to find for f, and we have here this f. This will happen if x minus x0 is smaller to delta 3. And now, as we've done before, we just take delta to be the minimum value between delta 1, delta 2, and delta 3. This way, if x minus x0 is smaller to delta, three things will happen. We'll have this condition, this one, and this one. So what we have was f of x times g of x minus L1, L2. We said that this was smaller than or equal to the absolute value of f times g minus L2 plus the absolute value of L2 times f minus L1. And now we're going to try and bound this. We start with f. We knew that f, if x minus x0 was smaller to delta 1, f was smaller to the absolute value of L1 plus 1. And so we're going to use this bound here. This will be multiplied by g minus L2, and then we just have L2 times f minus L1. And now we want to make this smaller using the bounds we found for g minus L2 and for f minus L1. So we have absolute value of L1 plus 1 times, we said that g minus L2 was smaller to epsilon over 2 times L1 plus 1. And here we have L2 and the bound for f minus L1 was epsilon over 2 times L2. So now we cancel the like terms like this, and we have that this is equal to epsilon over 2 plus epsilon over 2, and this is epsilon. So given any epsilon, we were able to find this delta such that if x minus x0 was smaller to this delta, that thing we wanted to prove the limit for, that is the product of our functions, minus the limit, is smaller to epsilon, and that is that the limit when x tends to x0 of f of x times g of x is the product of the limits. So let's finish this video with one last proposition, that is the limit of the division. We have two functions f and g with limits L1 and L2 in the same point x0. So then the limit when x tends to x0 of the division f divided by g is the division of the limits. Notice the importance of saying that L2 is different to 0, because here we will be divided by L2. The proof for this theorem will be left as an exercise, and it's very similar to the one for sequences. Remember that for those of you who follow me in Patreon, can find solutions to things like this, proof for this proposition, and for example also this example we have to prove, and to the solutions of all the exercises that were given in the videos with practice.